Okay, let's start. Good morning, everyone. Today is April the 27th. Welcome to IME 470 class. So first of all, again, let me stop the video and share my screen. Okay, so in the last class, we've mentioned, let me see. In the last class, we've mentioned the maximum flow problem, which is for a given graph with capacity. We want to transport the maximum flow from S, the sink, to the source to T node, the sink. So we've introduced the formulation about this, and we tried this model. Remember it, and here's was our solution, the one that we solved, the one we got it here, and also we mentioned that the applications mostly they're kind of like network, like transportation, this kind of like a flight crew, scheduling, power grid, this kind of problems. And today let's have a further look at the general model. So this is the general model, such that I want to maximize x0. And again, remember the notation: x0 is the total flow transported from node S to node T. So this is really the flow that I want to maximize. And xij is the amount of flow transported on arc I. And this xij is less than or equal to cij, which is the capacity on arc I, okay? On arc ij. So here in general, I should have for x0, for S node, this is, I should have x0, which is the total number of flow to be transported, should be equal to the summation of the j, in which Sj is an arc, the flow transported on all these out arcs. So for example, here I should have x0 equals to S1 plus S3. Sorry, x S1 plus x S3. Because totally from S I can reach node 1 and 3. So this part, let me see. Yes, this part means for all the j that from S I can get to, I'm gonna add the flow. I'm gonna add the amount of flows of xsj, and this one means for all the for all the nodes I that I can go to T, I'm gonna also add all the amount of flows of xit. It should be equal to xi0 again, the number of flow totally exists in the network. So if we have a look at here, we will have what? We will have x2t, 4t is here. x4t plus x2t equals to x0. Why? Because only from node 2 and node 4, I can go to t. And here you can see that if I write in this way, if I write in this way, say j is in, let's say this. Let's say j, where it is. Sorry. Let me re-add one text here. If I write here, say jt is in A. If I write in this way, then clearly my j equals to what? My j equals to 2 or 4, right? Because only 2t and 4t is in the arc set. Similar here, what if I write, let's say I si as also as j, sj as in A. So what do I have here? If I write in this way, so my choices of j is what? As 1 and 3, right? Because only S1 and S3 is in A, the arc set. Okay, so here we go. So that is how to understand the first two constraints here. And then how about this one? The third constraint. This constraint is actually a constraint for in equals to out. That for any intermediate node, the total number of flow incoming equals to the total number of flow outgoing. Okay, so this means for a fixed node I, which is can be any nodes other than S and T. In other words, this is an intermediate node. So for any j, which can reach to I, the summation of xij must be equal to the sum of any j from I to go to j, the summation of xij. So if we have a look at here, for example, let's randomly choose a node. Let's say choose node number 3. Node number 3 here, for example. So if I choose number 3, where it is, it's here. So from which nodes you can go to 3? I can go from S to 3. I can go from 1 to 3, and I can go from 2 to 3, right? So that I have x S3 plus x 13 plus x 23. And from 3, I can go to which nodes? I can go to node 1 and node 4. So the right-hand side is x31 plus x34. So this is what this exactly is the sum of, let's say, j3 is in A, the summation of xij. Sorry, xj3. This should equal to the summation, because I cannot write the. Okay, wait. Let me use a word. I think let me use a word is easier because this is a text language. Okay. Let me make it a bit smaller. Give me 1 second. Let me make it a bit smaller because I want to open the Word document here. Okay, let me open the Word document. Where's my Word document? Yeah. Okay, here we go. Okay, so as we just mentioned, we want to have what? We want to have for node 3, right? Which is right here. Node 3 is right here. So if I want to compare this one with the equation, I should have what? I should have sum of j3 is in A xij. This should be equal to what? Sum of also j. Here is j is 3j as in A x 3j, right? Sorry, here is xj3, not ij. j3. So this is for node 3. Okay, and very clearly for this, x3j is in A. Let me okay. So if I have j3 as in A, this means what? This means j equal to what? From which j3 is in A, j is s or 2 or 1, right? You can see s1, 2, or you can write s1, 2. It doesn't matter. You know, orders does not matter. And so what if I have a similar thing, say 3j is in A. 3j is in A means, okay, from 3 I can go to which node? I can go to node 1 and node 4. So here, if 3j is in A, so I'm gonna have j equal to 1, 4. See it? So this is an example for node 3, an intermediate node. And of course, you can do the same for any other intermediate nodes. Okay, so this is So this is the meaning of this equation, this formulation. And finally, of course, you have all the capacity, all the flow transported on edge ij must be less than or equal to Cij, the capacity on this edge. What I'm talking about, for all these kind of capacities. For example, let's consider S3. You must have X S3 is less than or equal to 13, which is the capacity. And finally, you have everything Xij is greater than or equal to 0. Of course, you cannot transport a negative flow. So this is the formulation. The first formulation we call MFP1. Any questions here? Any questions? No question? Okay. Then let's have a look at this. We actually have a similar formulation, which is almost the same except for here. You can see here, here, here. I have all less than or equal to. By comparison, here, 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 I have all equal to, right? And I claim they're the same. Can anyone give me a reason why they're the same? A very simple reason you can understand, actually. Any ideas? No? Okay, then let me directly explain it. Let me first ask you a question. Suppose I have an x, let's say this. Suppose I have, let's say, x is, suppose I have x as less than or equal to 3 and greater than or equal to 3. What is the value of x? Everybody knows that, right? X is both greater than or equal to 3 and less than or equal to 3. That simply tells me that simply left or right. That simply tells me that x equal to 3, right? Very clear, right? Everybody can understand this one. Okay, now let's have a look here. So what does this mean? This means that your outgoing, the flow that you're gonna go from, you're gonna leave x0, leave the source node here as at least x0. How about this constraint? The second constraint. The second constraint tells you that the flow entering the tail, or let's say entering the tank node, is at least x0. Okay, let's see here. What I know that leaving s going, leaving the flow, leaving s is at least x0. And here I tell you that the flow coming into t is at least t. And you see something interesting? That means the flow is less than or equal to x0. Sorry, here is less than or equal to x0, and the flow is also greater than or equal to x0. See here? Because this constraint again tells you what? This constraint tell. Sorry. I guess I made a typo here. Let me see. No, the key is correct. What I just said was something wrong. So this tells you that x0 is less than or equal to the real flow that's coming into the network. This is the second part here. Let me change the color to be let's see, blue. This part x0 is what? Is the flow that I want to calculate, and this part is what? This part is the flow that is actually existed in my network, right? So this tells me that the x0 should be less than or equal to the flow really inside in my network. Okay, now how about this part? This part means the total flow coming into T, right? And this is the actual actual flow in the network. Then you have x0 is greater than or equal to the actual flow in the network. See it? x0 is both less than or equal to and greater than or equal to the actual flow in the network. That means what? That means there's only one possibility, that x0 equals to the actual number of flow in the network, right? And hence, this is equivalent to this. Okay, and this is also similar. Why? Because again, we assumed that there's no loss or consumption, something about the flow because of this, the law of the conservation of the total flow. This is, our assumption. And hence, if I write in this way, the incoming is less than or equal to the outcoming. This and this, these two are actually the same type. This tells me what? There's only one possibility, that x0 equals to the total number of flows in the network, and the incoming equals to the outflow. The inflow equals to the outflow. This is something similar to this. Let me use another example. Say, where's my Word document? Here we know I have this, right? Okay, now let's have a look at the second case. Suppose I have, let's say this. Let's say x0 is less than or equal to, for example, I just randomly write something. Let's say x12 less than or equal to, let's say x31 less than or equal to, let's say x14. Actually, I can really write something here. Please, why so stupid this software? Let's say here, for example, my x0 is less than or equal to xs3, let's say. This is the amount of number, let's say, for example, s1 plus x31 plus x31, for example. And also less than or equal to blah, 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 less than or equal to 3. So this tells you what? This tells you only one possibility, that everything here, no matter x0 or s1 plus x31 or this dot, 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 all of them must be equal to 3, right? Equals this. Equals dot, 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 equals to 3, right? And this is exactly the meaning here. Here we go. This equation. I should say plus these two as well. And hence, these together tells me what? This tells me that less than or equal to is equivalent to equal to. And so MSP1 and MSP2 are equivalent. Although here, we wrote here as inflow equals to outflow, and here as inflow is less than or equal to outflow. But actually, they're exactly the same meaning. Okay, any questions? No question? I guess you may want to ask a question that since they're equivalent, so why should we write it into two formulations? For example, here, this formulation is really easy to be understood. It's great. So why should we have this formulation? There are two reasons. First of all, for most solvers, solving an inequality, let's say less than or equal to type of constraint, is much easier than solving this kind of equality constraint. The second thing is that later we're gonna introduce MCP, the minimum flow problem, and you're gonna see that one formulation of the minimum flow problem and this maximum flow problem as well. Sorry, the minimum cut problem, not minimum flow problem. The minimum cut problem. One formulation of the minimum cut problem is the dual problem of this maximum flow problem, and that leads to the very famous maximum flow minimum cut theorem. And that's the reason why, the second reason why I want to introduce this MFP2. Okay. Okay. Then how to solve the maximum flow problem? First of all, as we just mentioned here, this is what? This is a linear program, right? See, everything here is linear. You have x0, x0, you know, on the other side is the same, just the change of the constraint, you know, equality to inequality. See, everything's linear here. And hence, this is, of course, a linear program. So for linear programming, for example, I can use simplex method to solve. And number two is that there is a specific algorithm, a labeling algorithm. This is actually called Ford-Foxon algorithm. If you're interested, you can go there. Here's a Wikipedia link. This algorithm is designed for solving the MFP specifically, and it can do the work, you know, very efficiently. And that is, I think, that is everything about MFP in this lecture. Any questions about MFP? If you again, if you wanna say anything, please unmute yourself. Otherwise, I cannot hear you because everybody, when you enter the meeting, you are muted automatically. Any questions here? No question? Okay. Then the second topic of this lecture is minimum cut problem. First of all, let's see what does a cut mean. So a cut is a node partition ST by cutting some arcs here, such that node S is only in set. Such that node S is in set S, and node T is in set T. Here, S means the index set of nodes to which S can get, and T means the index set of nodes which can get to T. And we need to have S union of T as V, and S intersection of T as empty set. In other words, S and T are mutually exclusive, and you know, any node in the network must be belongs to either S or T. Must be exactly one of them. And the total weight of a cut is the sum of weights of arcs that are cut. Let's have a look at examples. You're going to see it more clear. Let's suppose this. So for this network, I cut this and these two arcs. I cut these two. I use a dash line. So what's going to happen is that from S, you can go to which node? You can go to nowhere, only yourself. So here I only have my S as a single node, S itself. And then from which node you can go to T? I can go from 1 to T, you know, 1 to T, 1 to T, 1 to T, okay. Or I can go from 2 to T, delta 2 to T, or 3 to T, the path is 3 to 4 to T, or 4 to T, which is delta 4 to T, or T itself, right? So from nodes 1, 2, 3, 4, T, I can go to T, and hence I have the T node, and hence I have the T set is 1, 2, 3, 4, T. How to calculate the total weight of the cut? That is the weight of the cut, of the weight of the arcs that are cut. So I cut these two arcs. The total weight is 29. By the way, for the minimum cut problem here, again, if I have a number on the arc, that means it is the weight, okay? And you can see for all the three problems, the network optimization problems that we have introduced, they are, let's say, SPP, shortest path problem, minimum spanning tree, and also actually 4, maximum flow problem, and here the minimum cut problem. 3 of them, which are the shortest path problem, minimum spanning tree problem, and the minimum cut problem, if I have a number on the on an arc or edge, that means it is the weight of this arc or edge. Only in the maximum flow problem, actually I used a parenthesis to make it, you know, different. Only in the MFP, this means what? The capacity. This is not the weight, but the capacity. Okay. So let's go back to the minimum cut problem here. So the total weight of the cut equals to 16 plus 13, because these are the two arcs that are cut. Let's have a look at this graph. So now I cut these two arcs, 1, 2, and 1, 4. So let's see what is set S and what is set T. Again, set S means index set of nodes to which S can get. T means index set of nodes which can get to T. Okay, so from S, if I cut in this way, I can get to which. I can, of course, S itself is here. I can go to 1, I can go to 3. I cannot go to any other nodes. So S set equals to S node, 1 node, and a 3 node. Okay, how about T set? From which nodes I can go to T? I cannot go from 1 to T, I cannot go from 3 to T. I can go from 2 to T, I can go from 4 to T, and the T itself, of course. So the T set equals to nodes 2, 4, and T. Then what is the total weight of the cut? I cut arc 1, 2, I cut arc 3, 4. So the total weight of my cut is 12 plus 14 equals to 26. See? Okay, and then have a look at this one. I cut arc 1, 2, I cut arc 3, 4. Sorry, I cut arc 4, 2, I cut arc 40. Then the same question. From S, I can go to which nodes? S can go to S itself. S can go to 1, S can go to 3, and also S can go to 4. The path is S, 3, 4. So my set S equals to S nodes S, 1, 3, and 4. How about T set? From which node you can go to T? I can go from 2 to T, and of course T to T itself. So T set equals to 2 and T, nodes 2 and T. For example, from 3 you cannot go to T. See, 3 to 4, and this one is cut already. This arc is cut. So only 2 and T, nodes 2 and T can go to T. So my T set is 2T. And correspondingly, my total weight of the cut is 12 plus 7 plus 4 equals to 23. Okay, so the fourth example is similar. If I cut 2T and 4T, these two arcs, then from S, I can go to nodes S itself, and 1 and 2 and 3 and 4. So S set equals to nodes 1, 2, 3, 4, and S. T itself, that's it. No one else can get to T, so set T equal to a single node, which is node T itself. And correspondingly, I have the total weight of cut equals to 24. Okay, so this tells you the definition of cut is actually a node partition to two sets, set S and set T. And again, T and S, these two sets are mutually exclusive. And each node in the graph must belongs to exactly one set, either S or T. You must belongs to one, and you must belongs to exactly one. Cannot be 2, cannot be 0. In other words, here I did make nodes S and T to be unconnected, or should be disconnected, Okay. And then let's have a look at the two ill-defined examples. Why is that ill-defined examples? Have a look at this graph. Suppose I want to cut the arcs, S3 arcs, 1, 3, 1, 2, 4, 2, and 4T. I cut so many arcs. Looks very strong. But what are your set S and set T? You'll have a problem here. Why? Because have a look at here. So from S, I can go to which node? I can go to S itself and node 1. So I claim here S equals to S1. And then how about T? From which node can you go to T? If I cut in this way, clearly only 2 and T, right? I claim 2T as set T. Everything looks good, I'm done. However, how about nodes 3 and 4? Because from the definition of cut, we claimed very clear that I must have S union T equals to V. In other words, each node must belong to exactly one set, either S or T. But if you have a look at this example here, how about the nodes 3 and 4? They do not belong to S nor T. Then that means what? That means it's a problem here. And hence, if I claim in this way, this is not a legal cut. See it? This is not a cut, not a ST partition. Okay. And then how about this example? So I cut in this way. This time I cut arcs S3, 1, 2, and 40. See what's going to happen? Again, the same question, from which node, from S, you can go to which nodes? Okay, I can go from S to 1, I can go from 1 to 3, so S to 3, and then 3 to 4, and then 4 to 2, and 2 to T. See it? I find a path from S to T. And again, this means what? This means it's something wrong. This is, again, not a cut. Why? Because a cut should be an ST partition that S is disconnected from T. Or you should say that we can say that each node belongs to only one set, either S or T set, right? But here from S, I can go to all nodes. And from any node, and also here, from any node, I can go to T. In other words, all the nodes here belong to both set S and set T. And this is not an ST partition because S intersect of T must be empty set. So it is wrong. So be careful about these two things, that you must guarantee that S union T equals to V, the total nodes, number of all the nodes in the network, and the intersection of S and T as empty set. In other words, each node must belong to exactly one set, either set S or set T. Did I use a big S here? I'm not sure. Okay, so in these two cases, they are not cuts. Any questions about the concepts, or let's say the definition of cuts and the weights of the cut among these two groups of examples? This is counterexample, actually. Any questions? No question? Okay, so let's have a look at the application of minimum cut problem. So first of all, the minimum cut problem means I want to get the minimum cost of the cut disconnecting two nodes, S and T. So this is the point of minimum cut, because maximum cut is somewhat easy. I can, somewhat, let's say, cut all of them. For example, I cannot claim it this way because theoretically, if I cut all of them, this is not an ST partition. But I can always, try to find, for example, here are my here are my examples. I can always, for example, cutting this way or cutting that way. That's very easy. But it's not easy to find the minimum cost cut. So we are more interested in the minimum cut problem. Okay, applications are, first of all, a very interesting thing is called image segmentation. I'm pretty sure you have seen this kind of, graphs like previously, like in cartoon. When I was a kid, I saw this kind of, a picture and make it to black and white, this kind of cartoons. And in, old time, people did it manually. So a human's gonna, take this part, for example, the shape of the plane out and put it in the black background, and you see, oh, here's a plane, and the plane is, taken out. This is a typical example of image segmentation. And also here, this is a CT scan, and you can see something here as kind of like abnormal, a CT scan of someone's head. Here's something abnormal, and you may doubt this might be a tumor, for example, or something wrong. And then is it possible we can use AI or use some algorithm to automatically detect it instead of using human's eyes to to manually check it? And the truth is, yes, we can do it. And this is this is related with the minimum cut problem, that you can define a likelihood function, at each node. Node here, some mostly mean, let's say, some pixels or some units of a small part of graph. And then you can do what? You can define a penalty function. The penalty function is exactly the minimum cut problem here, which is a weight here. Then you try to find kind of like an edge that has the minimum cost and the disconnect two parts. For example, here, I make it to two parts. One part is the plane, the other part is the whatever, the sky, or you can just simply call it the background, right? Here, similar, One part is a tumor, the other part is the regular thing. But to be honest, in terms of this specific graph, probably it's going to find the cut like this way, you know, the shape of the head, probably. Anyway, so this is how we can actually use the minimum cut problem to help this image segmentation. And the second example is something like business, I should say network attack and defense. This is typically applied in some military, you know, level, say military operations. For example, suppose consider, for example, this is enemy network, and I wanna let's say disconnect. For example, these are bases. This base from this base. How can I disconnect them? If I disconnect them, then you know we can weaken the enemy's network. The question is, of course, to disconnect them, we need to pay some costs, some operations as well. So I want my loss or my cost to be as small as possible. And meanwhile, the two enemy bases are disconnected. And this is the minimum cut problem. And of course, similar, we can apply this in some business strategy, you know, to kind of like disconnect some, you know, some nodes, let's say the supply chain or something else of my competitor. I know it's kind of like very evil, but that's the business. That's also the minimum cut problem because I try to minimize my loss or try to minimize my cost. Okay, and the more applications are actually related with maximum flow problem, because later you're gonna see the minimum cut problem is actually a dual problem of the maximum flow problem. I will show it probably next class or on Friday. Okay, so these are some applications. A question after it immediately is how to formulate the minimum cut problem. Because definitely you don't want to, you know, manually check the, you know, any graph, the minimum cuts by your hand. It's really difficult if a graph is very large. So we're gonna define two groups of variables. The first group of decision variable is a 0, 1, actually both of them are 0, 1 variables. The first one is z variable. Z equals to 1 if node I is in S, and z equals to 0 if node I is in T. So first of all, very clear, zs must be 1 and zt must be 0 because node S must be in set S, and the node T must be in set T. Okay. The second group, we define Yij to be 1 if I is in S and J is in T. Yij equals to 0 otherwise. So very clear, if I define this way, then if Yij is equal to 1, then the arc ij is cut, right? So after defining y, immediately I get my objective function. Why? Because if Yij is 1, then arc ij is cut. That means, yes, I need to count the weight of arc ij. And hence, I'm going to have the Wij times Yij and the sum for all ij are in the arc set. So summation of ij is in arc set Wij times Yj. This is going to be my objective function. Then how about the constraints? Because the constraints is kind of like difficult. Why? Because you need to guarantee that each node must be in either S or T. This is relatively difficult to formulate. And to be honest, when I just learned these kind of network optimization problems, I was able to formulate the other three problems purely by myself. It's not, sorry. There are the two. Actually, for the minimum spanning tree, I didn't directly formulate it. I did think of the MTZ, this type of constraints. Actually, the one I think I created by myself was not an MTZ constraint, as something like still a flow constraint, but use that constraint, I can detect a connected part. That was done by myself. However, to be honest, I failed to find the minimum cut problem by myself when I first, saw this problem. It's this idea. Finally, you're gonna see this formulation here is really simple, but it's really difficult, for you to directly get it. I don't know in history how people thought of, so simple constraints to directly describe the minimum cut problem. And it's really, really smart, I have to admit. Okay, let's have a look. So as we've mentioned, if Yij equal to 1, then clearly arc Ij is a cut. And if Ij, Yj equal to 1 by the definitions of my Zi, I must have what? I must have Zi equal to 1 and Zj equal to 0. Why? Because Zi equal to 1 means I is in node S. Zj equal to 0 means J is in node T. And here we go. The meaning of Yj means I is in S, J is in T. So I must have Zi equal to 1 and Zj equal to 0. However, if Yij equal to 0, then there are three cases. Why? Because it could be, for example, here as this case as what? This case is I in, let's say, both Ij. Ij is in S, right? So this is Z equal to 1, and Zi equals to 1, and the Zj also equal to 1. Or it can be the case here, both of them Ij in T. Both Zi and Zj equals to 0, meaning that both of them are in T. Or the third case is what? The third case is I is in T and J is in S. So I have Zi equals to 0 and Zj equals to 1. Zj equal to 1 here. So if my Yj equals to 0, I have these three cases. Then that's the problem. How can you formulate it? And a very smart observation is that no matter which of these four cases, including Yj equal to 0, including Yij equals to 1, I must have Yij is greater than or equals to Zi minus Zj. You can easily verify it. For example, here, this case, Yij is 1, 1 is greater than or equal to 1. This case, let me see. In this case, 0 is greater than or equal to 0. In this case, also 0 is greater than or equal to 0. In this case, 0 is greater than or equals to -1. You can clearly see it, right? So I can simply use this formulation, this constraint, to describe the relationship between Yij and the Zi and the Zj. And another thing is that since I must have Zs equals to 1 and Zt equals to 0, so I can write these two constraints to be this constraint. Zs minus Zt is greater than or equal to 1. Because your Zi's are what? Your Zi's are binary. So if two binary variables, Zs minus Zt, is greater than or equal to 1, that means what? That means there's only one possibility, that Zs equals to 1 and Zt equals to 0. You cannot find another possibility that the subtraction of two binary variables is greater than or equals to 1, right? So I only need to have these two types of constraints, and I can already formulate the minimum cut problem. Here we go. So the objective function is sigma of Ij in arc Wij times Yij. And the two constraints are Yij is greater than or equal to Zi minus Zj, and Zs minus Zt is greater than or equal to 1. Here means both Zi and Yij are binary variables. Clearly, the key variables here. And indeed, this is really, really smart. I would strongly recommend you, after the class, try instead of just directly accept this, let's say, constraint, accept this formulation. Try to challenge it. Try to say no. Try to always try to challenge the thing that you learned. And in my personal view, that is the best way that you can learn, because in order to say that something created is not the best or something created is not correct, you have to find a way to argue it, right? During the process, you are trying to find a way to argue it, you may learn the most. And if you are really lucky enough, you may be able to find a method which is better than the one showed in the textbook. And congratulations, you have changed something in the world. Great achievement. Of course, in most cases, you may not find it because this kind of theories are kind of like challenged by many people in decades. This formulation, I believe it was firstly proposed in 1970s. So already 40, sorry, that's 2020. It's already 50, almost 50 years. It's difficult, of course. But during this process, you can greatly understand why people thought of, this formulation. And that's really smart to actually use such a simple constraint to describe such a relatively difficult problem. Really smart. Okay, let's have a look at the constraint. Let's have a look at the problem for this specific graph. First of all, I have the maximum summation of wij, yij. So here, my arc is what? My arc are, for example, 16, 13, 10, 4, 12, 9, 7, 14, 4, 20. All of them, right? So here I just, there are too many, arcs. I just use dot to make it shorter. So here, what I mean is that the summation of, for example, 16 times ys1 plus 13 plus ys times ys2 plus blah blah blah. So the summation of all edges multiply the corresponding yij. Okay. Then let's have a look. I must have yij greater than or equal to zi minus zj for any arc. So for example, for arc S1, I must have ys1 is greater than or equal to zs minus z1. ys3, which is this one, must be greater than or equal to zs minus z3. y13, where's y3? Must be greater than or equal to z1 minus z3. And here we go. You just do all the same, all of them. And the final one is y4t is greater than or equals to z4 minus zt, okay? And then finally, do not forget the constraint here. zt minus zs is greater than or equals to 1. And you're going to have all the decision variables are binary. Okay, and due to time limit, I'm not going to show the Excel result in this class. We're going to do it on Wednesday. I think that's everything about today's class. Please let me know if you have any questions. Feel free to join my virtual office hours, actually called Zoom hours, the same time. And if you have any questions, please feel free to make an appointment with me by email. Relatively, our time, are more free during this remote education. So I think as long as you have a question, in most cases, I would have time. Depends on your time. We can make an appointment and have a Zoom meeting. That's everything. Thank you very much and have a good day. Bye-bye.